So my second talk will be a little bit different from the first talk because Maxwell asked me, this actually followed the presentation I gave at UCL about my work that I do there since I moved in summer. And he asked me to do a tutorial on dynamic causal modeling, which is a method for data analysis which I apply to multi-brain, so to hyperscanning data. And I wasn't quite sure what everyone's background is going to be, and I'm still not quite sure what you guys are all working on and what you're interested in. And so my goals for this presentation was to give you an idea what DCM is, what it can, but also what it cannot do, for you to decide later on if it fits to answer the questions that you might have on your data. So we will go through the entire analysis from specifying models of brain function, going to the group level, and some other nice extras that we can do. And of course, I brought some, as I call them, hyper DCMs. So I applied this to hyperscan data, and we're going to look at this. And I try to balance it out between background information and also what does it look like when you try to apply it, because I understand that not everyone is interested in seeing 20 slides of equations, but you just want to know, is this going to answer the questions that I have? Okay, so just so everyone is on the same page, when we talk about connectivity in terms of the brain, then people speak about different kinds of connectivity. In structural connectivity, we assume that we measure direct white matter tracts between region A and region B. Functional connectivity does not care about a direct connection between the brain region, but looks at something like statistical coherence. So a lot of the measures that we saw in the previous presentations are examples of functional connectivity, so where you just look for some form of similarity or dependency in your data. DCM is a method to look at effective connectivity. So the effect that one brain region has on another brain region. So it's a direction of influence, and we infer causality with it, even though I don't want to get into the whole discussion of what is causality in the brain and all this. Okay. So on the first level, the subject level of dynamic causal modeling, you start with usually some brain regions you're interested in, based on some task effects or some group differences, or your prior knowledge, or in my case, I'm always interested in TPJ, as you now know. And you can specify these brain regions in DCM in terms of a matrix. And we assume some connections between these brain regions. Can you see them? Okay. We assume connections between the brain regions. But we can also specify some external input, that we call the driving input, because for example, if you have a task, when with each trial of your task, it pings the brain regions into activity or changes of activity. And we can also specify the so-called modulators that will change the connectivity between brain regions. This makes sense. So for example, if this brain region is a brain region that processes language, and this would be some primary visual area, and you have a task where you present either some information, either by using pictures or words, then it makes sense that you have your language region, the connectivities to some higher order processing region be selectively modulated if you present language, right? But not if you just present pictures. And this is already the full first level DCM model that you will spend most of your time specifying. And we take good care in specifying. Oh, also we assume some self-connections of the brain regions that we need. So brain regions can change their activity over time, or that activity can be modulated. Okay. So in terms of applying the data, what you need to do is, first of all, decide which brain regions are important for you. That gives rise to the vector Z, that is just in rows, all the brain regions that you're going to look at. And then you're going to specify which connections are present in your brain network, so all these gray arrows. And that is the so-called A matrix. Also, we want to specify this external or driving input that elicits changes of brain activity, that is in the C matrix, and the modulators in the B matrix. Now, of course, we specify all our input, which is a so-called U matrix, and regardless of whether it's driving or modulating, you just have to remember later in which order you put it in. Now, a full model of the brain is usually not so useful because, as you see, it gets quite messy. And what DCM is going to do is it's going to estimate one parameter for each connection that you have, for each modulation, for each external input, and it's going to fit one model that includes all these parameters and it's going to try to predict brain activity from it. And many of these parameters are not going to do anything. So your model fit is going to go down. This is not a good model of the brain. So you can reduce this model and say, for example, if this was our language region and this was our primary visual region, that we might not need the connection between the two because they're not going to speak to each other, but they will only be in contact with the higher order processing regions. We can prune away these connections and some modulations and assume that only these regions receive the driving input. And there you go, you have a really nice, clear, simple model of the brain connectivity that is going to be very much easier for you in terms of interpretation of your output at the end. Okay, now something that is, I think, really important for this network is that what you specified now is the neural model. So we have the network architecture and all the stimuli that's going to change brain activity. But in almost every neuroimaging method that we use, we don't actually measure brain activity. Especially in fMRI, what we measure is some approximation to brain activity, which is the Bolt signal, plus we measuring a bunch of noise. And DCM takes this into account by specifying having one model that includes all these different elements. And what we just specified is the neural model that gives rise to the actual true neural activity. This is what we are actually interested in. And this is what we will later look at. And in terms of this network, this enables us to nicely integrate different modalities or also from different tasks and simulations. So the so-called forward or generative model of DCM tells you how the brain activity, how we moved on from brain activity to the data we actually acquired. So the neural model elicits some brain activity, so brain cells firing or not firing. And they use oxygen to do that. And so we have to provide this oxygen, we have a change in the hemodynamic parameters, or we have a hemodynamic signal, which then later gives rise to the Bolt signal, which is what we are measuring using fMRI, or try to measure. But we, oops. I'm going to try to use the mouse, I always click. We don't measure it, we measure the Bolt signal plus some noise. So DCM does these three things. We have the neural data, which is the only thing we're interested in. We have an so-called observation model and the measurement. And what we do now is when you know what the network looks like and the stimuli, so the whole neural model, then you can predict brain activity from that. You're going to predict what's going to happen in the brain due to the task or the conditions or whatever you fed in. And DCM does that and compares it to the true data that you acquired. And it's going to try to fit the parameters so they very accurately predicted the true data. And many of the parameters that you see there are the same ones that we use, it uses Bayesian inference to do that. And so we're working with the same parameters in our simulations, in our in silico models of brain function as we do here in DCMs on hyperscanning data. Since there's technically a couple of different settings of these parameters that could equally good predict the time series, we use something called Bayesian model comparison to compare different models and figure out what the best one is. So I'm not sure. So, and I was pretty sure I'm not anymore. If people really want to get into the mathematical details of it, but just as a quick summary, is we separate our signal into the neural sources and the non-neural sources, so the noise, and we specify the state of our brain region or brain network as a function of the network architecture and some input that we specified. And this is the non-neural sources are a summary of the hemodynamic model and some known noise like scanner drifts, or it depends on your modality, and some mouse is gone, unknown error. And since we specified this in terms of matrices before, we have the famous neuronal state equation that explains you how the state or the activity, the state of the network at any given time point was a result of, again, the architecture and its modulators and the driving input. And you can blow this up for the entire network, and then we have the bilinear state equation. Yeah, I think I just skipped some of the math stuff.
Isn't that very similar maths to what is done in structural equation modeling?
Structural equation modeling does have some of the advantages because it has a full neural model, and also I think a hemodynamic model or some similarity between it.
SEM, you can divide into a measurement model, an error model, and a signal model.
Yeah.
That's the same. You have your same arrows and
right.
nice little circles, covariance.
Yeah,
and you do it like, and those are then represented as matrices.
Yeah.
Like the way you showed.
I still have I did have a slide comparing the different models. What structural equation modeling does not have is the input, so you cannot compare experimental conditions. And also, I think it didn't have the dynamic part, so you get one value for the entire time series, if I remember right.
It's ordinary form, it's the state, you'd have to use a growth curve.
Yes, something like that. We can look at it in the detail. More questions? Yes?
Sorry, I'm not meaning to be picky, but what's the J exponent on the B?
On the B, that's the condition that you have. So we had pictures and words that combined make up the task, and you have one B matrix for every condition that you want to compare. So you could, for example, say, let me just go back to this. So you could say that a specific region is only modulated when I show subjects pictures, and another one with words, and that's why we have two separate B matrices for each condition that you can specify.
What I find kind of confusing in this kind of Bayesian model comparison,
Yes.
not only in DCM but generally, is that it's very dependent on our choice of model space. So I mean,
Yeah.
we can just select 10 really bad models,
Yeah.
and one of them would be
Yeah.
the best.
Yeah.
So it's
The best of the worst.
There's a couple of things. So on the subject level, it's important to look at the model fit in terms of the explained variance that you preserved.
Mm-hmm.
So did you specify a model that actually explained the data? And I also brought, if you're interested in it, I managed to mess up my DCMs completely after presenting it at UCL. I got a lot of tips and I put everything in its perfect new model. And I explained nothing anymore. I had explained variance between 0 and 1%. So that's the researcher's life. So I knew that was suddenly a very bad model. And it took me a good 2 weeks to figure out what was wrong with it. So you were right. So there's that is on the subject level. You need to check that you're explaining your data well. And on a group level, we have other methods where you use auto reduction, for example, where you compare any sets of parameters just depending on so the only error that you can do is specifying the wrong brain regions, and it will automatically look for connections that are meaningful. And you don't specify the meaningful models anymore. We will look at an example of that as well. But you're right. DCM, this is one of the important things. DCM is a method for hypothesis testing. So I think a couple of years back, I was starting with hyperscaling. I would have not used DCM because it was so exploratory, and I didn't have good hypotheses on what a network would look like. This is luckily different now, and I can state hypotheses and make a useful model. But yeah, if you don't have a educated guess on what the network is going to look like, it's going to be garbage in, garbage out. And there was a question. Oh, I'm sorry. Yeah.
I was just wondering, I don't know if that's assumption where it comes from, but why is the non-neural source, why is it not a function of itself, like Z? Like Z is a function of itself.
Y is a.
So I would say that the non-neural sources would also influence themselves.
But
It's not a differential equation here.
oh,
No, I'm just asking why it's not a function, why it doesn't exist.
It's just y, it's not y dot. So I think it's just to prove that you don't simulate the dynamics of the.
It just doesn't matter, you know, maybe.
No, but if you take Z dot, then
Yeah.
Z becomes a function of itself also.
Yeah, okay.
yes, but the hemodynamic, like this hemodynamic part, at one point doesn't influence the hemodynamics on the other point, does it? So it's
Oh,
not.
is it? I don't know.
Isn't it
Maybe
like a
not.
fixed? It's like the same for templates. I don't know. We have to.
Yeah, it's just a question, I don't know the answer, but it's just, I was just wondering what the motivation was. Yeah.
I can find out if you like. The DCM super expert happens to sit in my office at UCL, and I bug him with questions like that all the time. Yeah.
Okay. Yeah, I guess maybe that assumption is kind of hidden in one of the original papers.
Probably. Well, we can. No. Okay. We discuss it later. Okay. So our goal is to find the best model that has the best prediction of the brain activity, and there are different combinations of parameters, like I said, that potentially could explain the data. And so we have to quantify other characteristics of our model, not just the accuracy, but also we quantify uncertainty. And that starts with specifying so-called priors or prior expectations of what our parameter is going to be. And initially, when you set up your network, you specified if the connection is present or a connection is not present. So is it switched on or is it switched off? And if you switch on a connection, this means we have an expected value of 0, but we have a non-zero variance. So we allow the parameter to move away from 0 if the data supports it in order to predict the data accurately. But having a high variance means that we are very uncertain about this parameter, that is actually 0. And having switched off the connection means we have an expected value of 0, but also a variance of 0, so the parameter is fixed at 0. We are super sure that this parameter doesn't do anything. It's still part of the model. Okay, so what we want to do is maximize the probability that we've seen this data given some model. So we want to maximize the model evidence. And we can't infer this directly, and so we use an approximation to it, to the model evidence, called the negative variational free energy. And if you've ever heard Carl speak about anything, then you've heard the variational free energy, or the free energy principle. And inverting a model or estimating a model gives you two things. It gives you a probability density over all the possible values a parameter can take on, and it gives you a value of the quality of the model, which is called the free energy, and it means the accuracy on how well we predicted the data, penalized by the complexity. So if we have a very complex model with very parameters, with many parameters that had to move away from the prior, then we have a very expensive model that we don't want. We want the simplest and best model. And that's what you do. You invert models and you compare them in terms of their free energy. That's a repeated thing that we do in DCM. We specify models, estimate them, compare the free energy, and whoever has the highest, most positive free energy, that is the best model that we can have. And that's something really nice about DCM, because as long as you the input data that you put in is the same, you can change the neural model as much as you like in terms of the input, in terms of the connectivity, the parameters or the connections that you have, and you can compare everything using free energy. So it's really useful, especially if we don't have an educated guest. Yes?
So like in terms of complexities, like the size of these matrices would change?
The size is always the same because it's defined by the connections that you have, and these are either, so some of the matrices either take on the value 1 if you switch it on, or 0 if you switch it off. And the parameters themselves then will be estimated. The size will be the same, but the number of parameters that are non-zero will be not the same. So you will have a lot of parameters that are non-zero. So this is the typical output where you have all parameters for the A matrix, so the structure of the network, and the B matrix, so your conditions. And each of these parameters means a connection between two brain regions. So for example, from region 2 to region 1. And this will be one parameter that will be estimated. And we will get the posterior estimate for here. This is connection parameter number 14, and you can then look it up. Which one was which one was 14? And we have here we have a number of parameters. Sorry, the mouse keeps disappearing. We have a number of parameters that moved away from the prior of 0, but only a few ones that are meaningful in terms of these pink bars are the 90% confidence intervals on how confident we are that this prior is non-zero. And we only look at the parameters that we are confident are not 0. So you only have this one, maybe this one, and this one. So this is like 17 or 18. This would be 14 and 13. Would be parameters that deviated from 0. If you have many parameters, then this is a very expensive model because you have you had to have many parameters included. And we usually don't look at this level of analysis because it's first level, subject level. We usually want to look at some group mean, and you will see that it's a little bit more cleared up there.
Sorry, I've just got, I have a relative discussed calculator, I just got lost. Can
Okay.
you explain where I've got lost?
Okay, what
What
did you
I
get?
don't understand
Yes.
is, given that every parameter is varying individually and is therefore independent, is by design independent of every other parameter because you can do what you want and you're then running across. I don't understand how that equation corrects for multiple comparisons.
Very nice. We don't correct for multiple comparisons because we don't have to, because we're not accumulating alpha errors. I had a big discussion with this about Peter just before I left, actually. But we don't need to correct for multiple comparisons because we're not testing based on like alpha and beta levels. I'm not sure if I can explain it very well, so I would just leave it at that. That we don't have to.
It sounds like that's something I'll have to take as given for now and go and read it.
Yes, you're gonna have to believe me. I checked it because I'm also, coming from a non-computational background. I know that I always correct everything for a bazillion models that I do, and so yeah.
To me, that looks like a set of an infinite number of models or a very large number of models within a defined model space, rather than a single individual model. But I'll accept
The
that.
model space, I think I took out the slide. Never mind.
Okay then, but at least it's not just me not understanding it. That's really.
Yes, it's really different. Well, we could spend the whole week talking about the background of DCM, and I've been working with for 4 months now, and I've gotten kind of like I can stand on my own 2 feet.
When you say it's not alpha, is it fair to say it's not really that you're creating a distribution and testing the distribution, it's that
No.
you're testing the fit in each
Yes.
model, so it's more
That
like
you
a
just take the
bootstrapping
model
or
fit.
convergence process
Yes.
than it is saying, here's a distribution and this is the part of it that's I mean, that's a
Yeah.
little my understanding.
Like my attempt at an answer would be that that's the reason we need variational free energy, because you can always define the gradient on every parameter. Doesn't matter where you are in the model space, you can define the free energy gradient.
Oh, I see.
So that's like the
Right.
kind of magic of free energy that you
Oh,
can
yeah, because
always
I-
change your.
Yeah, because basically, that's just an expression of the gradient, it's not a direct measure of alternate probabilities, you're just talking about the gradient
Yeah,
on
you
the
just have
surface.
going through the landscape, but you're never sure whether you're in a local minimum
Yeah.
or there may be a better one somewhere.
Okay, I got it, so we're not talking about really about probabilities, but
No,
about
no.
gradients on a probability surface.
Yeah,
Yeah.
Yeah, okay,
yeah, movements on a statistical manifold.
yeah, okay, I got it now, makes sense. Sorry.
Separate
I didn't
question.
understand it.
So I'm just curious, I mean, if you can do this on an individual subject level for each model, then, I mean, it looks like it tells you right there which connections look like they could be meaningful.
Yeah.
Right at the single subject level, right?
Yes.
So I mean, why not just do a fully connected model on each person, take only the connections that show non-zero values, could have non-zero values, use that as your reduced model, and then just do that for, like as opposed to doing BMC only at the second level, right? Like, I don't understand why.
Well, this is already a form of Bayesian model comparison on the first level, but you mean why I specified a reduced model in the beginning?
Well, so I'm just saying, like if all connections, if you just include a fully connected model here, then
Yes.
when you do the estimation, it tells you, what
Yes.
connections to keep.
Yeah,
Then-
but
then
this
you're
might
not
be
doing
different.
BMC between two different pre-specified models, right?
Yeah, but this might be different across subjects, right? Or subject groups for that matter. So if you take it to a second level or a third level, there's different ways. Then you want to, just like in group level and classical SPM analyses or GLMs, you want to find the common parameters across subjects. So this might be just like in this particular subject a meaningful connection. And if you there have been. If you look at older publication on DCMs, what people did is they actually did specify separate models on the first level, and then took the optimal model onto the second model, but you had local optima, so you were non-comparable because there were different models. So it's easier to stay with a more complete model, one subject level DCM, take it to the second level, estimate the parameters and your group difference or whatever you want to model, and then reduce from there. And then you know that you have all your subjects included with their parameters, and you will have some form of average parameters.
I see how to do it at the group level. That's something like you kind of have to do, it seems like.
Yes,
But-
and if you reduce the model on the first level, you're stuck with this model, and you cannot compare different models on the second level that have different connections.
Right.
But here we have, because another individual might not have this parameter, might not have the same value, but there's a different, if you switch off this, in a separate subject level DCM, if you switch off this parameter, it's gone. But if you have it still in there, you allow it also to be zero. Even if the variance is non-zero, it can still be zero in a given subject. So taking that to the second
I
level.
see, okay,
Yeah.
okay, that makes sense.
Okay, we'll see it with some data. Maybe it's easier to understand. Did I miss? There were many hands. Did I miss someone? Okay. So there used to be a picture that was meaningful. It's just a summary. So we're already done with the first, the full first level analysis of DCM. And like I said, it's the part where you spend most of your time fiddling with the models and trying to get a very precise and very good model for your given data, your sample or your task or whatever it is. And the steps are that you specify a neuromodel. That gives rise to some brain activity, but we can measure directly brain activity, so we treat them as hidden states. And so we turn this into an observation model by regarding the HRF function. It's also done, for example, in SPM analysis, as anyone works with this. We estimate the models and compare them, and now we're ready to take them to the second level. Okay. So usually we are not interested in single subject effects, but we have questions on our data, such as what is the average, for example, average model across all subjects, or is there difference between my patient groups and my control groups? Or you have some super cool covariate that you're interested in. For example, the social network size, does it do anything with the level of brain synchrony that someone achieves? And these are typical second or group level questions you have. And we use something called parametric empirical Bayes to answer these questions. And PEP, the abbreviation, just assumes that all the first levels, so this is an index for the level, not the power. So the summary of all my first level connectivity parameters. You can join, we still have space. It's just a linear combination of some group mean, your design matrix, so your group difference or your social network size, whatever you're interested in. Other covariates that we know, we usually control for age and sex and stuff, and some random error. So it's very similar to any second level analysis that you might have done using SPM or other approaches. And what we do is we just summarize all the subject level parameters, and this is where GCM especially takes the values of the parameters from this first level, but also takes into account the uncertainty that we had. So if you go to a group level, a subject with very noisy data, where we're uncertain about the parameters, will be penalized in terms of when we estimate the second level parameters. And this is not the case if you use other methods like so PEB I think was only introduced this year or not too long ago. And you just took the second level parameters and then had the problem that you had some heavy outliers and then changed your entire network. Yeah, and then you just, PEB is a hierarchical model of the brain function, and we already know the bottom one. We assume that the brain activity we saw is a function of the DCM and its parameters, some known and unknown noise. And on the second level, we assume that all the first level parameters are just a result of the second level parameters, some noise, and the design matrix. And in terms of applying DCM, or doing PEP analyses, group level analyses, all you have to formulate on the second level is just a design matrix. And if you've ever had any boxcar function or covariate analysis in SPM, it's exactly the same. It couldn't be easier. This is a typical design matrix. So PEP always assumes well, all the regressors are in a column, and the first column is usually expected to be a vector of ones, and that would give us something like the group average or the group mean, or what you asked about. So what is the typical network look like? Which are the important parameters? This is called the commonalities in DCM. I don't know why it's called commonalities, but never is referred to as a group mean or the first column. The second column and the following columns will just be your group difference or your covariate, whatever you're interested in, or you're controlling for age and sex and whatever. And this is what you have to specify. Yeah, and it's super simple. And we do the same thing. We estimate our models, called model inversion. And this gives you two things. It gives you the group level parameters for your second level, and also gives you a measure of the group level free energy. And the free energy on the group level is a little bit different because it takes into account all the accuracies on the subject level, but the complexity from the first and the second level, and has some combined factor of the hierarchical model. And you can feed in, as you will see for the hyperscaling data, different types of design matrices and compare which is the best one for your data. And this is a typical output for second level parameters. So in the first 9, they only took in 9 parameters from the model. And these are all the effect of the first column of the design matrix on their parameters and the second column of the design matrix on their parameters. And you can, these are beta weights, so you can, interpretation is just like an effect size in this case. So for parameter 16, which is, I don't know, connection between region 2 to region 1, under some condition, for example, is different between groups if that was your second column with the effect size of this much. So you have a very clear interpretation of your output as well. Okay, now reducing models. That is a question we just had. Should we reduce the model on the subject level, or can we do it on the group level? And there's something very elegant called Bayesian model reduction, where we can either specify some plausible reduced models for the group level, estimate them. This takes only just a few seconds, so we get the free energy. And then again, find out which is the best model for our data. Again, the most positive, highest free energy is the best one. We compare our full model with some reduced models and get some winner. And this will then give you a probability matrix over the reduced models for each column of or the first two columns of your design matrix, and you can then hopefully have a winner and say, oh, my group average is best described by this full model, for example, but my group difference is better described by some other model. And what I now think in terms of do we really have an educated guess about social brain function, but I think is a very maybe the better method is auto reduction. So you can not specify these reduced models and just tell it to get rid of all the parameters that we don't need to accurately simulate our data. And it will then go over all, yes?
Yeah, I just want to check I've got my understanding correct.
Mm-hmm.
That while you haven't got problems of multiple comparison at the level of building the individual level, because you're descending a gradient, here at the level of BMR, you have got problems of multiple comparisons if you keep specifying different models and run BMRs again and again.
But it's the same as on the first on the subject level.
Is it the same?
You're again doing but you're technically doing the same thing. You're specifying the model and only comparing their free energy, and you're not doing like
doing
testing
multiple comparisons even there. So you could, in theory, do an infinite number of different models, and that would be an accurate thing.
The auto reduction is actually just that it takes the combination of all parameters you put in, switched on and off. Well, it's a greedy search, so a little bit different, but so in theory that could be 10 billion different models if you have just a few number of parameters, and it takes some reduced version of it, so the best models of that.
I will go away and read some more. Thank you. I've obviously still misunderstanding it.
Okay.
Oh, yeah.
Oh, yeah, sorry.
Can I ask you a stupid question?
There's
Seems like a tree structure, like in the group level when you're talking about in the subject level, it's just like leaves of this tree or something like that, or is something
I missed the beginning. So what is with the structure? What did you say?
like a tree, like you have some like groups and then leaves of each group is like subject.
You mean for the reduction?
In
or-
general, how is like the whole structure?
I don't think I'm
Each
understanding the question right.
group has individual related to the whole group.
So what defines the model is its connectivity, basically, right?
Yes.
So the full model is everything connected to everything with all parameters activated. But when you do your BMR, some of these models, like parameters, they explain nothing, right? So the reduced model is the model that basically explains the most with the least amount of connections. So that it's not quite a tree structure because it's starting from the full connected model, and then the paths down
Yeah.
are not like they're pruned models, right? That you remove connections. So like at the bottom, basically you're left with like a node connected to itself,
Yeah,
I guess, right?
it goes through all the parameters. So it starts with one parameter and then looks at all the combinations of other parameters, and then it will stop if the exclusion of some parameter makes your free energy worse, and then it goes through all the parameters and defines the best model like that. So it's a stepwise research. I'm just not sure if I understood your question correctly.
I was just wondering, does the Bayesian model reduction take into account the identifiability of models? Because sometimes a priori, there's a structural model that's equivalent to another, and so even with optimal numerics, you would still have issues with identifiability because there's equivalence. Does that make sense? Or even
You mean
subparameters
equivalent in
cannot
terms of?
be determined and things of this nature?
You mean equivalent in terms of explaining the data, even though the structure is different?
Yes.
Yes. Well, you in the auto reduction especially, you will average across these. So if there's 2 or 3 models that are the best, or in the auto reduction is out of these 10 billion, it's the 256 best models, and will average the parameters across these very good indistinguishable models. I don't know who was first. Max Pastor, decide.
Go for it. It was just also, it seems so too good to be true, like,
I'll show you what it looks like later.
how you avoid to have like, how you assure that you're not overfitting the data,
Yes.
and how is the out of sample generalization assured?
Well, we use the priors to prevent overfitting. Yeah, that's sort of go into detail with overfitting. So there's always, Jesus, I also had a slide on overfitting and why we're doing that, and Peter said don't do that because nobody's going to bother. But yes, or we have the priors to prevent the data from becoming, so we can penalize too complex models that would not be generalizable anymore.
So that's integrated in this free
Yeah.
energy
Yeah.
optimization.
It's in the priors.
So, it has to do with, so it's basically a fundamentally different way to do modeling, in the sense that you pack all your assumptions into the priors, so you don't have to correct for alpha errors, etc., because you already put all your, like, let's say, reservations about things that are far from your expectations, put them in your prior views. Because, the standard method where you do alpha hypothesis testing, then you assume, for example, that if it's 5% or less the probability, then you reject the null hypothesis. So that's like kind of a prior that says, okay, if my data is so unlikely, then the null hypothesis is rejected. So by default, the null hypothesis is like has more, you have more confidence, and the alternative, you get closer to the alternative when it's like 20 times as likely. Okay. That's the null hypothesis. That's like the standard method, but here you turn that around. You put those assumptions in your priors, and then you don't have to worry about that whole the alpha value.
So I got it for the alpha. That's more like for the out of sample generalization. Are you assured that if you take an independent sample of subjects, you would have the same model that's going to be selected in the free energy?
You mean for every time you select an independent sample?
No, like for instance, in machine learning approach, now you have you're forced to have an independent cohort replication. So is the free energy principle like minimization handling that internally? Like you don't have to have a separate samples to assure that the model you have doesn't will generalize to another population.
Do we ever know this?
What?
Do we ever know this? With any of the models? Well, you can do like a validation approach within your data, like leave one out.
Like leave one out stuff.
For example.
Okay, so there is like stuff
Yes,
like
yes,
that
yes,
after.
yes.
Okay, that's what I.
Yes.
Okay.
Just cognizant about time constraints. We have 15 minutes left for the talk.
Okay.
So-
should I go?
So maybe we should just power through to make sure that we can finish on time.
And look at the hyperscale data. This
Yeah,
is
exactly.
actually why we came, right?
Yeah.
Okay, so you're just gonna have to believe me about all the claims I made about DCM today. Yes. Okay.
There you go.
There we go. So, hyper DCMs. So, like I said, I've been using, I moved to London in summer, been using DCM and Bayesian inference since then, and it is one streamline of my work on trying to model or get more complex models about human social interaction within Bayesian inference and using active inference or multi-agent models for that. And DCMs is the method I use for analyzing the data that I already have. And I will show you some of the problems and some of what it looks like. So this some of the advantages of DCM is that you can, once you have your neural model, it doesn't matter what type of modality you're doing hyperscanning with or what type of task you have, you can always work with the same models. A huge advantage is we use Bayesian inference, and I think in the free energy principle. And I think during the week we will hear a lot about people who work on in silico models of interaction, of multi-agent models, and DCM is just a method of it works in the same environment, and so we can nicely feed it into each other and test our models on actual data and get more precise models of our data using the in silico models and so on. For some people, it's important. It's it's for free and it's fully implemented into SPM with all the support that you get. But I think it also came up in the questions that a big problem is that you need to have hypotheses, so the possibilities are endless, and you will specify first-level DCMs for the rest of your life if you're not able to have some educated prior assumptions on your networks. And also in my data, I saw that the effects we're looking for, group differences in a hyperscanning framework, across brains and complicated tasks, are going to be so hard to get. We have to get really precise models. You can have this, I can send around this slide if you want to get into DCM and read a little bit. I highly recommend Peter Ziedman's work. He just published 2 tutorial papers this year, one on subject level and one on group level analysis. And on his GitHub page, you find everything. His updated step-by-step guide and data and the papers also. Okay, that was it. These are some of my